off, we're talking about machine learning in ArcGIS. So we learned last year, maybe the year before, I'm sure it's been at least a year or two, where we figured out if we could put machine learning in the title of all of our sessions, we would double attendance. Because who doesn't want to learn about machine learning? It's certainly all the buzz these days. And I'm kind of torn, because on one hand, I totally understand why it's all the buzz, because it's really cool and exciting. On the other hand, I always get nervous that we're getting distracted by shiny objects, and that we should be focusing on solving problems. So hopefully you will find that I'm less worried that I individually am being distracted by shiny objects, and more that like we as a whole are being distracted. And so I'll talk a little bit about, I think, some of the ways we should think about these tools, some of them, the ways that we've been thinking about them on our side as we develop them. So speaking of all the buzz, there's a lot of words flying around about all in this area of machine learning and AI. Whether it's, and a lot of it kind of gets confounded, right? It's packages, it's modules, it's methods, it's algorithms, it's ways that computation happen, all kind of jumbled together in this big soup of concepts. And what we want to do today is kind of focus in a little bit. We're going to focus in to kind of these three terms that are linked. You've got artificial intelligence. Within that bubble of artificial intelligence, we have machine learning. It's a subset. And then a subset of that, which is deep learning. You kind of see a lot of talk, machine learning and deep learning kind of talked about separately, which isn't wrong. Technically, deep learning is this kind of sub-discipline within machine learning, but especially right now, we see deep learning being kind of used to solve a very specific set of problems. Machine learning kind of more broadly generally applies to a broader set of application areas, and we'll talk a little bit about some of that. There's a lot of work being done in this area of AI or artificial intelligence beyond some of the things that we're working on. And actually including some things we're working on that we're not going to talk about today, things like natural language processing. There is some research being done within Esri in that field of natural language processing that's more on the side of user experience than it is on the side of like spatial analysis. We're definitely going to be focused today on using these techniques to do spatial analysis. But of course, machine learning and AI are being used in all sorts of ways, things like looking at unstructured text to find location data. Yes, that's a very interesting and useful application of AI, but what I'm interested in is taking that data and then doing something useful with it, turning that data into information using some of these methods. And so that's definitely going to be our focus today. We are really going to be focused in these two areas, machine learning, and we will talk a little bit about deep learning. This is where the majority of our research and development is happening within Esri in these two spaces. And we'll talk a little bit about that. So what is machine learning? In the context of ArcGIS and the tools and techniques that we're going to talk about today, it's really a set of data-driven algorithms and techniques that automate processes to do things like prediction, classification, and clustering of all sorts of different kinds of data. And within those categories, there's a really broad range of applications. Now, I do think it's important in a very similar way when I talk about statistics and spatial statistics. I think it's important for us to distinguish between traditional machine learning and spatial machine learning, just like we distinguish between traditional statistics and spatial statistics. So traditional machine learning methods, these are methods that you can certainly use to apply to spatial data, but they aren't in any way, they're not built in a way that takes into account the spatial nature of your data. Your data is essentially a table of numbers, and the traditional machine learning techniques are using that data to find patterns, find clusters, make predictions. But the spatial characteristics of your data aren't part of those algorithms. Now, that doesn't mean that they're not appropriate for really complex and important spatial problems. There's been a lot of research that's shown that some of these traditional machine learning methods are very effective for solving spatial problems. So a really good example of that is the random forest algorithm. How many of you guys have used random forest at some point? It's really powerful, really awesome algorithm or approach, and it's not spatial at all. But there's been a lot of research that's shown that it's very good at modeling spatial problems anyway. So that's a great example where it's a method that's out there. It may not be spatial, but we put it into ArcGIS because we know it will be useful for the problems that you're trying to solve. We also think a lot about how we can take those traditional machine learning methods and try to implement them in a way within ArcGIS that makes it really easy for you to use them on spatial data. And for you to incorporate spatial data into them, even if the algorithm itself isn't spatial. So allowing you to easily do things like integrate lots of data sources, vector and raster data together, calculate distances on the fly when you're doing your modeling, things like that. Then there's spatial machine learning. And these are methods that inherently take geography into account, whether it's in how we measure what it means to be neighbors. A lot of these spatial machine learning techniques and spatial statistics techniques have at their heart Tobler's law, the first law of geography, that things that are closer together are more related than things that are farther apart. And that by acknowledging that truth, that things that are closer together are often more related than things that are farther apart, we can actually more accurately model complex phenomena because we are acknowledging that fact about the features in our data. And so we are definitely, I would say, a large portion of our R&D efforts are in that space of spatial machine learning. That's where those are the problems that we care about solving, and that's really kind of what differentiates the tools that we build from a lot of the other packages out there. I also think it's worth mentioning that machine learning is not new. Deep learning, actually, is not new. How many of you, more than a decade ago, knew about or used in some way a neural network? Bunch of hands went up, yeah. I work with a bunch of people who 30 years ago wrote their dissertations about neural networks. They will let me know often about that as we talk about these things. And it's true, these things have been around for a long time. The algorithms aren't new. What's new is that we can actually use them finally. They were great in theory back then, but we didn't have the computational power to really see what they were capable of. Now, because of things like distributed computing, but really just if you think about the capabilities of just a basic laptop that we have compared to what was possible 30 years ago, this is basically a supercomputer. And we're capable of doing a lot more computation now. And so a lot of these methods, which are incredibly computationally intensive, they are inherently data-driven. And by being data-driven and a lot of times being based on lots of permutations and trying lots of combinations, that's at the heart of a lot of these methods, they require a level of computation that is finally possible. And so we're seeing this reawakening of machine learning and deep learning and AI because of that, which is very exciting. I do think, before jumping into some of the tech and the really exciting demos and talking a little bit about all the tools that are in the software, one of the reasons that we wanted to give this workshop, I think last year was our first year giving this workshop, and one of the reasons that I wanted to do it was because I really wanted to talk a little bit about the fact that we have a lot of machine learning tools in ArcGIS, and we actually have for some years, and we're actively in development for lots of new ones, but many of you have been using machine learning for a long time. How many of you would consider yourself a data scientist? There should be way more hands up. I mean, maybe it's my bias, but you guys are data scientists. Our community has some of the most capable spatial data scientists in the world. These tools that you've been using, they are powering data science. And I really want you to walk away feeling empowered to do some of this sophisticated analysis and to know that the analysis that you're doing is already data science. It's just a new term we're using for something we've been doing for a long time, which is actually really exciting. I think it's great that there's so many people that are finally getting excited about analysis. We've been excited for a long time about analysis. But there is one really important thing to remember, which is that when we go to solve a problem, we really want to focus on what's our data and what's our question and what's the problem we're trying to solve, right? No one's problem is that they need machine learning algorithms. That's not a problem you're trying to solve, right? That's like saying your problem is that you need big data. No. Maybe if you have big data, you need something to do with that big data, but no one needs big data. It's a problem we're trying to solve. We need to get away from our focus on, if it's not a good analysis unless you're using some latest and greatest algorithm that just got invented, right? And more on, is the algorithm you're using appropriately solving your problem? Are we approaching this problem in the best way possible? And there's actually a really important concept in analysis about simplicity and parsimony. We want to solve our problem in the simplest way possible. Not simpler, but not more complicated either. The more complicated we get, we introduce all sorts of factors. So it really is important for us to focus first on the problem that we're trying to solve and then figure out which methods are going to be the most appropriate. We don't want to find ourselves being a bunch of machine learning tools walking around looking for problems, right? We want to have a problem first and be looking for a solution. So within ArcGIS, we want to focus on kind of these broad categories of classification, clustering, and prediction. And really by prediction, I mean predicting of a continuous variable. Classification is really another prediction type where you're predicting a category. And we're going to talk about each of them. So we're going to start by talking about clustering. So clustering, you can think about it in a couple of different ways. One might be that we're clustering just based on space, geography. Another might be that we are clustering based on a combination of space and attributes. So we have a multivariate analysis, but we also want to incorporate geography. Another way we might cluster our data is based purely in that data space, where we just have attributes and we want to find natural clusters in our data. Or we might take a more kind of traditional statistical approach and ask questions about patterns that we're seeing and comparing those to null hypothesis, like complete spatial randomness. So all sorts of different ways that we might explore clustering in our data. And Alberto is going to show us a couple of examples of clustering in ArcGIS.
Okay. Hi, everyone.
Wait.
Oh, sorry.
What are you?
I am 4.
4.
There we go. So our first example is going to have us take a look at some check-in data in San Diego. What is a check-in data point? Let's take a look. So these are just entries where people have checked into some location at some point in time. And this might be interesting if you're looking for something to do, not sure if tonight, because tonight is the Thursday night party, but at some point during the user conference. And this is just essentially a map of points. So let's take a look at how density-based clustering can assist us with trying to figure out perhaps some fun locations in San Diego that you may be able to visit, because so many people have checked in there, that might be an interesting location, right? So it's going to take all of these points and essentially classify them as either part of a cluster or noise. And the tool is quite straightforward. You can pass in your check-in data, determine your output feature name, and then this is where you determine one of the 3 clustering methods. It's almost 3 tools in one. Let's start with a simple assessment of what a cluster may be. So let's say we have the requirement that a cluster is composed of 100 features per cluster, all within 1 mile. So this is my first crack at this problem. How do we make a little bit more sense out of these check-in points? And behind the scenes, actually something that I always mention during all of these demonstrations, if you're looking to learn a little bit more about the tools, this lovely icon over here at the top right, click it. It'll take you to the documentation, and the spatial statistics team does a lot of work on making sure that it's easy to run these tools and understand the concepts behind them. So now that we have our outputs, let's take a look at what this looks like. We have a little bit more information now, right? So there's these gigantic clusters kind of in San Diego and north of San Diego, but there's these other regions that are now a little bit more interesting. So let's zoom into one specific region. This is a mall, and it's called Westfield North County, and we had a cluster that was found there. There's also another mall that presumably is one of the most popular here in this area, and this was another interesting region. But actually what I want to point out is that if you have a study area that encompasses both a dense urban environment and perhaps a more sparse rural environment, you're going to have to think of clusters with different definitions, right? A cluster in one context may be different from a cluster in another context. So the second way to run the tool, HDBScan, adjusts that definition of a cluster for you. And I'll just show you the output of that tool. Let's go ahead and collapse this. And we see a little bit more granularity in this downtown area. So let's go over here to the convention center, actually. It's pretty neat that it was able to discern these different regions, such as the convention center itself as a distinct cluster with check-ins, also the hotel nearby and the marina, and also the gas lamp district. So it's starting to almost find these little regions, these neighborhoods, just naturally through the data. And the clusters that I was able to find here in downtown San Diego are quite different from the clusters in rural San Diego. I didn't really have to subset my data and run it multiple times to do that. I just let the tool determine that. And then there's a third option for density-based clustering that goes into something called optics. Optics gives you this cluster sensitivity parameter. I'll go ahead and show you the output. So cluster sensitivity lets you really tweak what your clusters will behave like. But it also works with a concept called a reachability chart. And a reachability chart is quite useful. Let me collapse this so that we can really see it. It kind of helps you explore these valleys and peaks that may determine the start of a cluster or the start of a noise point. So if I select all of these guys over here, this is that big monstrous cluster here in downtown San Diego. Perhaps I want to increase the cluster sensitivity and make some of these peaks rise above the kind of like the water level that determines whether you're a cluster or noise. And simply by running the tool again, you can start to get a little bit more granularity there. So there's our new reachability chart, increasing the cluster sensitivity. And then I increased it all the way up to 90. So it's a range between, I think, all the way up to 100. So in this case, let's go ahead and expand that chart. You see with that chart that that monstrous cluster that we had in the default run of the tool has now been split, and there's all these little mini peaks and valleys that were determined there. And optics is quite useful if you have a good sense perhaps of whether a cluster may be in one part of your study area and you want to use that definition and apply it across the rest of the study area, or really get more granular with this chart and take a look at why things are being categorized as clusters. So that's one example of clustering. Another example of clustering that works with attribute values takes a look at blood banking data in California. And in this case, what we're looking at is essentially blood transmitted diseases in California. And this is a problem that works with hospitals or blood banks. The goal here is to essentially create these regions, to do spatial optimization so that every region gets a balanced proportion of these blood transmitted diseases. Because the problem is that if you're a blood bank and you have a disproportionate amount of blood and transmitted diseases, that may impact your supply and then maybe incur a greater demand for that blood that other regions now are not able to, or are getting an unfair, essentially, quality of their blood supply. So we're going to start actually with one type of clustering called spatially constrained multivariate clustering. And this is just to get a sense of the clustering of attribute values for a few different types of blood transmitted diseases. I'm going to pass our California blood data, and I want to cluster by a few different types of diseases. First, it's going to be MRSA. the infection rate in 2017. Next is going to be CLAB, which is infection rates that were caused by at the hospital when you've actually had transfusions at the hospital. VRE, another type of bacterial infection, so let's go ahead and select that in 2017. There it is. And finally, West Nile virus for 2017. And then we're going to also specify that we want 10 clusters in this case. So there is a mix of attribute clustering, and it's also making sure that each cluster for these 10 clusters is spatially contiguous. And this tool really you need to explore both with the output layer, but also with one of the charts that it produces.
How many of you guys are familiar with k-means? It's a pretty common multivariate clustering tool. This is kind of like a spatially constrained k-means is how you can think about it, trying to find groupings both in data space and then also spatially.
Yeah, and in this output, what's sort of interesting is that this one cluster, this red cluster, in the coast happens to have pretty low values for all 4 types of infectious diseases or bloodborne diseases. So you're probably in a good state or in a lucky area if you happen to live there. But there's these other regions, perhaps this cluster over here in the north is categorized by having a really high rate of MRSA infections, or this other region over here that stands out because of VRE and actually pretty high West Nile virus. So what the goal is, though, is remember, we want to tie it back to blood banks. And we want to determine for each of these blood banks, we want to create these territories that are as balanced as possible with respect to these types of infectious diseases. So it's almost like the opposite problem, right? In spatially constrained multivariate clustering, you're separating data by how similar it is within a cluster and how dissimilar it is without a cluster, right? In this case now, we're going to do a little bit of the opposite. So it's actually a great privilege to introduce one of the new tools in the spatial statistics toolbox called Build Balance Zones. So let's go ahead and take a look at that. Actually, let me go ahead and run it. So Build Balance Zones works with the concept of, it's well named. It will build balance zones based on a series of attributes. So let's go ahead and pass our blood data. And you have the ability to create zones using an attribute target. Perhaps you don't want, if you're creating sales territories, you want every territory to have the same amount of population or demand supply. In other cases, such as this one, you may want the number of zones to be specific, and you want the zone building criteria to be based on those infectious disease attributes. So let's go ahead and establish those. So we have MRSA, we have CLAB 2017 once again, we have VRE 2017, and finally West Nile virus. And you can apply a weight as well. There's additional zone selection criteria. So if you want the zones to be equal area or as compact as possible or as equal as possible the number of features, you can select that and it'll try to optimize that as well. So let's go ahead and run the tool. And what it'll give you is an output with quite a few charts. So what's interesting about all of these tools, I feel like there's multiple outputs, right? Not just this layer that gets produced in the table of contents, but also the messages has a lot of information that may be conducive for you to see. So it gives you a little bit of information about the variables that you passed, but you also get this output layer with the different zones that it was able to find and different charts that explain that. So let's see the distribution of one of these variables and dock this. So these are potential territories for each blood bank. And for the distribution of one of those variables, MRSA infection rates, perfect homogeneity would be where every value would be pretty much the same, right? But this was the best it could do with all the other factors that it's now considering. So it's not going to find the perfect answer for every variable, but the most optimal answer given all the different factors that you pass to it. And finally, there's additional things that you can consider when you run the tool. So if we go back to the tool, perhaps you want to incorporate the amount of beds for each blood bank, beds available. Or you want to pass distances to each blood bank, and you want to consider, sorry, let me scroll down here. distance to consider is a parameter that would actually compute the distances to each blood bank and would try to optimize there as well. So I can briefly show you some of the outputs if we start to bring those other factors in, such as diseases, beds, population, and income. And you see that originally, if we compare back to just diseases, there's this region over here in the coast that is now being changed to now include parts of the inland regions of California, because we're also optimizing based on the beds, the population, and the income. So this is a really interesting tool, especially for things like sales territories and other types of activities like that. Okay.
Okay. I mean, one of the things, I always push that button by accident. A couple things that I think are worth pointing out that are particularly apparent in the clustering tools is that, so how many of you have ever used density-based clustering? It's something, how many of you have used it in like R or Python package? So I'm sure you noticed that when you run it in our Python package, you definitely don't get a pretty output like this that has done the work of making sure colors aren't right next to each other so that you can interpret those clusters and see where those clusters are. You also don't get charts as part of your output that you can automatically kind of immediately start to use to interpret the results of your analysis. So that's some of the things that we put a lot of thought into. We try to really make that aspect of your analysis simple, to make the visualization useful and to create the right diagnostics so that you can immediately evaluate the effectiveness of your model, whether it's a reachability chart or those parallel box plots that Alberto showed for the multivariate clustering. So in addition to clustering, we've also got classification. So classification, there's kind of a broad range of things that fall into this category. I think probably in a room full of GIS analysts, when we hear classification, we probably all think about things like land use classification, land cover classification, very much kind of imagery classification. That's definitely part of it. There's tools like maximum likelihood, random trees, and support vector machine that are there specifically for image classification. And I'm sure some of those names sound familiar to you, things like support vector machine. It's a commonly used machine learning algorithm. It's been one of the methods available for image classification in ArcGIS for quite some time. And so those are there. There's some new tools for doing classification, and this is a different kind of classification. The term classification applies not just to something like imagery, but actually it also applies to prediction of categories. So another tool that's in ArcGIS called forest-based classification and regression. This is where you can predict a category. So it might be land use, that's a category, but it might be the pass-fail of a restaurant or the presence-absence of a disease or a particular species. So lots of different kind of ways that we can do this kind of classification. And I do think it's worth mentioning that forest-based classification regression and random trees, both of them are versions of the random forest algorithm. We can't call either of them random forest because the term random forest itself, the actual words random forest, are trademarked, which is somewhat shocking to me, but it is. The algorithm, however, is not trademarked, so it's the same algorithm you would use if you used random forest in any other package out there. We just call it forest-based classification regression because we have to. But hopefully you'll find that using it is actually quite different than it is in most of the packages that you might use out there.
Okay, so let's take a look at another demonstration. This time we're going to use forest-based classification and regression, focusing on the classification side of things, to look at a species distribution model, which lets us determine whether a species is going to be in a study area or not, or the probability that it will be in a specific region of that study area. And in this case, we're going to take a look at in Oregon at the Ochoco National Forest, because the Oregon Biodiversity Information Center provided us some good data for the presence of a species called Lomasium ochocense, but I'll just say Loma ocho because that's way too long. And in this case, these are presence points. This lets us determine these are field-validated locations where that species, that plant, is known to exist. It's a pretty rare plant. So the goal is to actually determine where in a much larger study area that spans about 10,000 square miles will this species be. It's a classification problem. So in order to classify, we're going to run forest-based classification and regression. We're going to need presence and absence points. We have the presence points. We also have absence points signified as green. And we're going to pass that as our input to input training features. We're going to keep the prediction type train only because really we just want to assess the quality of a model first. And we're going to predict presence. Now this is a categorical variable. We just want to determine if it will be present or not, or estimate. And then from here, we need some explanatory variables. So in this case, we're going to take a look at a few different characteristics, like the elevation. It could be a raster. It could be a raster that specifies the distance to a stream at any location, or climactic water deficit, the presence of canopies or coniferous trees, and a bunch of different slope characteristics that come to us as rasters. And in this case, we have that. So here's the elevation raster, the distances to streams, climactic water deficit, canopies, and so on. If I wanted to bring that into our model, I can simply hold Shift, select all of these rasters, and drag and drop them into explanatory training rasters. And if you had a categorical raster, perhaps land cover classification, you could select that checkbox there. You also have additional options, so you can create your output train features if you wanted to see how they would be classified. For now, I'm going to actually take a look at advanced forest options, and there's an option to compensate for sparse categories. If you notice back in our input absence, presence points, it's pretty unbalanced. There's a lot more absence points than presence. And what this will do is it'll ensure that every little tree in that random forest has both categories. And then there's also a number of randomly sampled variables, and that gets into how many of these rasters get considered for each decision tree, et cetera. So you can configure it quite a bit if you're experienced with the tool. If you're not, it picks some pretty smart defaults. So something that's really powerful about these tools, I love me some Python, but it's really great to just run these tools and have some smart defaults to test and just make some progress towards an answer, right? So running this will let us see kind of just a basic model to assess. And I'll spoil the surprise a little bit. This model is really good, not because of really anything I personally did. It's more because of NatureServe. There we go. It's just about done. Let's take a look at some of the diagnostics. There we go. And let me expand this and make it a little bit bigger. So you get a lot of model characteristics. Something that you may want to look into is how out-of-bag errors occur. My recommendation is take a look at the documentation. But you also get top variable importance. So if you want to determine which factors help explain the species and configure those and refine for your next model, you can take a look at these and how they factor into each decision. And then also the confusion matrix and different things from how we assess classification models. As I said, this model is quite good just because of the information that NatureServe provided us. So one thing that you may want to do is actually predict. This just gave you the assessment of a model. So you can change to predict to raster. And in this case, you get a few more parameters. In that case, you would have to name an output prediction surface and make sure that you have a match between the prediction and the training rasters, right? Perhaps if you're predicting to a different study area, you may have a different set of rasters and they may be named differently. You would just configure that here. But in this case, we know we just want to predict to the study area, and the elevation, et cetera, rasters match the extent. It does take a little bit longer to run, so let me just show you some of the outputs. So let's dock this over here to the right and see it side by side. If we zoom in over here to, there we go. If we zoom into the areas where we know the plant Loma Ocho is known to be, there's a few additional areas that are very similar or that could be good targets for validating. But if we go to the far west of that study area, these could be additional targets for additional field visits and so on. One final thing that the tool does give you, as I mentioned, a lot of the outputs no longer are just these layers, but you also get charts that help explain additional factors related to your model. So in this case, we have, let me make this over here. Let me dock it all together. There we go. So we have this chart that gives you that summary of variable importance. And you're not just going to build one model and stop there. You're going to keep refining, and this is quite useful to make those decisions. And that is classification.
Okay, so another thing to note is for each of these topics, we could and have throughout the week been giving whole workshops. We could actually teach probably a whole semester-long course just on each one of these topics. So this is kind of like a whirlwind tour of what's possible. I think sometimes it's really useful to just have a sense of the art of the possible, and then you know where you can dig in deeper. We have a lot of workshops available, videos, our PowerPoints available that dig into all of these pieces. So if we do succeed in getting you excited about something and you see an immediate application for something you're trying to do, we'll point you towards some of those resources at the end. So next is prediction, and really what we're talking about here is predicting a continuous variable. Now there's a lot of different ways that we can think about what prediction is in the context of spatial data. Sometimes it's interpolation. We have known values, and we want to predict between those values. And that phenomenon that we're trying to model is very, very spatial. So how many of you have done interpolation before? How many of you have used the wizard, the geostatistical wizard? Okay. So one of the tools that's definitely falls into this category is empirical Bayesian kriging, or what we call EBK. And EBK is a really powerful, very data-driven approach to interpolation. Anyone who's done interpolation using that wizard knows you quickly have to become something of an expert on interpolation. You're setting sills and nuggets, and it's quite a process. EBK takes a lot of that kind of out of your hands. It's very much, it's a very powerful method, partly because it takes a local approach to interpolation. Generally, the way that interpolation works is that there's a concept that there is some relationship across space, and that relationship is kind of constant across space. That semi-variogram is constant across space. But what EBK does is it creates these local subsets, and it creates lots and lots of semi-variograms. And what that does is it allows for those relationships to vary across space. And that happens, right? If we think about pretty much anything, most spatial phenomena also have some local component to them. So what we found is that using that kind of local approach, we get really, really accurate results using something like EBK. There's also now one of the latest releases in 2.4 has EBK 3D. So you can use EBK to do 3D interpolation on sample points that happen in 3 dimensions. There's also aerial interpolation, which is largely about kind of taking data from one set of polygons, creating surfaces from those polygons, truly taking into account the structure of those polygons, and allows you to do things like put that data into a different set of polygons with a different spatial structure. There's EBK regression prediction, which is kind of like a multivariate EBK, where it's under the hood using EBK, but also allowing you to use covariates that say if you add these additional variables, we can even improve the accuracy of those predictions. Then outside of that, there's also a bunch of different tools to do things in the realm of regression analysis. So there's generalized linear regression, which allows you to do regression analysis on continuous, count, and binary data. Also geographically weighted regression with all 3 of those same model types that allows you to do that same kind of linear modeling, regression modeling, but in a similar way with a local approach. And then there's forest-based classification and regression, which not only does classification, but also does regression for continuous variables in much the same kind of workflow that Alberto just showed us for classification. So he's not going to show us random forest again, but he is going to show us some of those new tools like generalized linear regression and GWR. Okay,
thank you, Lauren. So now we're going to take a look at house data, home sale values in the Washington State region near Seattle. These are a lot of points, and basically what we're trying to create is a model that may predict house sales. There is a chart type, a newer chart type called the scatter plot matrix in ArcGIS Pro. And this will help you examine the relationships between all these different candidate explanatory variables between each other. So one aspect, if we take a look at price and take a look at what things that price variable may be related to, there's a few candidate ones that stand out: square foot of the living area and the amount of bathrooms. But if we take a look at, and bedrooms perhaps, if we take a look, we have to actually make a choice between square foot of living being multi-equilinear with bedrooms or bathrooms. So if we take a look at square foot of living and bathrooms, they seem to be telling the same story. So if we're going to focus on a linear relationship, we have to make a judgment call. I'm going to focus on bedrooms and square foot of living to explain price. So let's go to our tool called Generalized Linear Regression. We're going to pass our input house data. Our dependent variable is going to be that price. You do have the overhauled models that you can create with it. It can be continuous, binary, or count. We're going to keep it continuous because it is a continuous value. And then there's the two candidate explanatory variables, bedrooms and square foot living. Once you run it, you're going to get a few additional diagnostics. So maybe we can, let's see. There we go. So the first layer that gets produced, the default symbology, is showing you the standard residuals. And we can visually see that they're pretty clustered, meaning that the tool is doing a pretty poor job in the areas where it's really dark green or really dark purple, and a better job in the areas that are a little bit light. So we're missing some information to help explain sale prices, right? So we may want to iterate a little bit and try to test other ways to predict home sale values. Another example is GWR, geographically weighted regression. And this will really make local models that you work with neighborhoods and fit a line for that neighborhood. So let's take a look at what that may look like. And actually, something I forgot to do, which I always talk about, is to look at the tool messages. So let's do that before we move over to GWR. There we go. So just on its own, it's not the only thing you should look at, but one of the main things is the adjusted R squared. So it has a value of 0.5, not quite great yet, but perhaps we can iterate, as I mentioned. If we now run geographically weighted regression, this is the output of the prediction looking at the standardized residuals. And if we look at the tool messaging for that run, you run it pretty similarly, but you do have to make some decisions about how you're going to make your neighborhoods. But the tool also has some smart defaults for how to do that. For now, what I'd like to briefly focus on at a high level is just the improvement between GLR and GWR because of those local models. Over here, you have an R squared of 0.87. So the fact that we're now telling stories for each local region is actually greatly improving this model. You also have the ability to, briefly, we'll take a look at random forest prediction. We're not going to look at it in great detail since we covered it for classification, but it can also predict home sale values. And there's some new things that you can do with forest-based classification and regression when you do regression. In this case, there's, if you pass your input training data and say that the variable to predict is price, and it's not categorical in this case, one of the validation options is to calculate uncertainty. And when you calculate uncertainty, it basically will run the tool several times and pick some of the best iterations to actually predict. So let me see if I can show you that through a chart. There we go. So this is, after I dock this, we should be able to see this a bit better. Sorry, just about there. Okay, so what this chart would signify is that in the lower ranges of price, we have a series of intervals where the random forest model predicted home sale values. But as prices get higher, there's actually a lot less predictability. It's a lot more uncertain. And we have fewer samples that are that expensive, so the variability there gets a little bit tougher to deal with. So it can help you when you're assessing the quality of a model. Looking at a chart like this and working with that uncertainty can help you assess where you can trust the model and for what ranges of your prices you can trust it. So that is a look at prediction.
And we actually have one more session this afternoon where we're going to talk about forest-based classification and regression. We'll get into a couple more details there. But lots of different ways that we can kind of apply either a traditional machine learning method like random forest, or a much more spatial method like geographically weighted regression. And one of the cool things about geographically weighted regression in that example was Alberto's random forest model that he trained actually included like 10 variables, which is great because you can just throw everything and the kitchen sink into a method like random forest. But with GWR, we got pretty much the same accuracy in our prediction with only 2 variables by basically allowing those models to vary spatially, which is very powerful. Worth a mention is that we also use machine learning quite a bit actually behind the scenes in a lot of our tools. So one of the things that is really important to us is making sure that as many tools as possible and for as many parameters as possible, we have really good defaults. So for instance, for the spatially constrained multivariate clustering tool, we use a concept called evidence accumulation to automatically give you probabilities and give you a sense of the level of confidence that you have in which cluster you ended up in. In optics, we use another technique to read that reachability plot and figure out a good default cluster sensitivity. Or for EBK regression prediction, we use principal components analysis to reduce the dimensions of the extra explanatory variables that you give it, so we don't have to worry about data redundancy or what we call multicollinearity when we go into that regression analysis. So lots of different ways that we're kind of behind the scenes without you really having to worry about it or even know about it, that we're using some of these machine learning techniques to give you really good results kind of the first time. Now, there's also a lot of work being done right now for deep learning tools in ArcGIS. Now, these tools are largely focused on classification and object detection right now. That's a lot of the deep learning tools have their roots in kind of computer vision types of problems. And the new ArcGIS Learn module, which is part of the ArcGIS API for Python, is exposing quite a few really exciting, very widely used deep learning methods to you in a kind of way that will be very familiar if you're using the ArcGIS API for Python. So they wrap the PyTorch library, which is a very widely used deep learning library, and also add a lot of value in that wrapping, both in terms of the user experience, also in terms of smart defaults, in terms of diagnostics that are provided back to you. So, and just in terms of kind of staying within the ArcGIS ecosystem so that you can easily go back and forth, not have to worry about taking your data out, bringing it over to PyTorch, learning PyTorch, bringing it back in. It really simplifies that whole process. So the ArcGIS Learn module is very exciting and something that's kind of a very active area of development for us. And Alberto's going to do a super quick demo of that.
Okay, thank you, Lauren. So this example will be using an ArcGIS notebook to show ArcGIS.Learn being applied to land cover classification using satellite imagery. And this notebook kind of gives you a sense of the table of contents, the different parts to this process, and it's really conducive to learning from an example, right? So this will be kind of quick. I think it's more helpful if you actually take it through your own paces at some point, perhaps in the expo. In the beginning, we really just import the ArcGIS API for Python here, and we're going to prepare some input raster data. In this case, it's going to be NAPE imagery, and that will serve as part of the input. The other part of the input is going to be a label layer with land cover classification. So let's take a look at those two maps side by side. So over here in the notebook, I'm going to use a little widget called HBox to show two maps side by side. On the left, we have the land cover, or the nape layer. On the right, we have the land cover classification. Continuing on, then you can start preparing your analysis to train a model using ArcGIS.learn. And this is a series of cells that essentially connects to a data store. And then using ArcGIS.learn, there's a submodule called export training data. So this will work with the input nape layer and the input label layer to create image chips, which the model would need essentially to train and learn from. So this is an example of the input chips and the input labels that get assigned to each chip. If you look at it side by side, this is actually what it would look like a little bit. And from there, then you can use a few different algorithms within ArcGIS.learn to train your model. There's a unit classifier available to you. The little hint that I have if you use Jupyter Notebooks is if you don't know how it works, you can ask a little question mark at the end and it loads some of the documentation that's available for that submodule. And continuing on, then there's a utility to help find the learning rate for that model, and it does plot that. Once you know a good learning rate, then you can do a model.fit, and it'll, for however many epochs you pass to it, it'll essentially train and try to minimize loss. Eventually, you get to a model that will try to apply that learned algorithm essentially into a new data set. And this notebook ends with a brief example looking at a specific area outside of the training region. That's a quick view of that example. If you want to look more perhaps at the Expo Island, they have other examples that you can take a look at.
And another big part actually of that the R&D that we're doing in this area is creating sample notebooks that you can use to get started and learn more. So some of those are already included as part of the new hosted notebook that's built into Enterprise. And so there's a whole set of gallery notebooks there. There's a lot of work to very quickly get those into the kind of outside of Enterprise onto the web, and as part of the beta that's going on for hosted notebooks in ArcGIS Online, you can also use that as a way to kind of get started in this area. So if you're interested in being part of that beta, you can kind of check out down at the Expo, or you can reach out to one of us and we can help you get started there. The kind of final piece of the puzzle here is about integrating with external frameworks. So I got on my soapbox earlier. I have a couple of them. This is definitely one of them. I got on it earlier and I talked about the importance of thinking really critically about the problems that we're trying to solve and not stuffing problems into a method just because we heard about it. In that same vein, I'm a firm believer that you should use the best tool possible to solve your problem. If that's in ArcGIS, that's wonderful. If it's not in ArcGIS, you should still use that method, the best one to solve your problem, right? And we know that it's not always going to be something that we've implemented. So there's a really strong focus on making sure that we make it really easy for you to go between ArcGIS and all sorts of other packages that are out there, whether that's big machine learning packages like TensorFlow or PyTorch or scikit-learn is really popular, or R. It's another big, how many of you guys use R? Lots, very, very common in this space also. And so there's lots of ways to do that, whether it's the ArcGIS API for Python or using ArcPy. We also have the ArcGIS Bridge, which is a big part of this integration story, and of course notebooks. So lots of different ways to think about how you integrate, what makes sense for your workflow to get your spatial data in and out to some of those other packages, how you can still take advantage of either ArcGIS on one side of that workflow, whether it's for visualization, data exploration, for further analysis, just for the sharing of your results, lots of different ways that you might still need to incorporate ArcGIS into a workflow. And there are tons of additional resources. We've got lots of Learn lessons and workshops that we've taught on these topics. So definitely we can kind of learn more. But Alberto's going to show us something pretty cool, which is actually another kind of notebook, which is an R notebook, which is another way to integrate.
Awesome, thank you. So this is an example by our colleague Oren Aiden. He's not here right now, but I think I have the same haircut he has, so I think we'll be okay. But this example is an R notebook. How many people here have used the R ArcGIS Bridge? Okay, great. Hopefully you get a chance to use it before the conference is over. And in this case, the R ArcGIS Bridge is really an integration between R and ArcGIS. It's an R package, and it lets you interact with your geospatial data, whether it's in a file geodatabase, a shapefile, a service, a raster mosaic, et cetera. It lets you work to integrate it in and out of R or ArcGIS. And over here, in this example, we're going to simply import it as an ArcGIS binding. Then using arc.check product, it'll authenticate with, or it'll determine what type of licensing you have. So if you have ArcGIS Pro, it'll give you all the details associated with that. And I have a file geodatabase here named seagrass.gdb. The goal of this notebook is actually to predict the presence of seagrass given a study area. So if you pass the GDB name, then it'll actually assess the path. It'll give you some information about the contents, the feature classes that are available to us there. And it's really as simple as doing arc.open. To get a data frame into it, I have a feature class here called EMU Global 90M. And there's a utility there called arc.open. I can pass the file path to our feature class, and then do arc.select to get a query. If you're familiar with R, you work perhaps with data frames already. And that's really the main gist of how to get feature classes out of a file geodatabase and into an R data frame using the R ArcGIS Bridge. So this visualizes our data, but going forward, you may want to work with raster data as well. So there's also methods for using arc.raster to get raster mosaics or whatever imagery service you may be working with. And in this case, we've loaded some of those rasters over here into the notebook and visualized them. Again, it's just through the integration with, through the R ArcGIS Bridge, we're reading straight from the file geodatabase and bringing them here into the notebook to plot them. So there's a few different explanatory factors, such as distances to major ports, et cetera. And then once you have all of these different factors put together in the notebook, over here, R has a utility called maxent that can be very useful to model the presence of seagrass. In the work that Oren was doing, he explored how that model could be useful for that purpose. And then once he ran maxent, the goal was to essentially bring the output, which is visualized here. This would be the probability of seagrass presence. The R ArcGIS Bridge would then let you bring those outputs back into ArcGIS using a few utilities. So over here, we're going to write the data back into the geodatabase and call it maxent prediction. So it's really useful if you're very used to R utilities, or even Python actually, because of the use of an R package called reticulate. You can actually work with other ArcPy functions to really have this one-stop shop in some cases to bring a lot of different tools and get data in and out of ArcGIS into R. So this is a great tool. Okay.
And Oren actually released a blog right before the user conference on how to get an R notebook set up. So if that's something that's interesting to you, you can check out that blog post. Just to kind of finish up, we do have a lot of areas of active development in this space. We're working on some tools to do time series forecasting, space-time interpolation, lots of new work in deep learning. There's some work being done on data engineering. There's also kind of platform level work about integrating some of those popular packages. The hosting environment in ArcGIS Online for those hosted notebooks is a big part of that. Also integrating Spark and exposing other Spark libraries. PySpark is a popular package that's also used in this space, and so bringing some of that in. And our major focus from a research perspective is definitely continued innovation, particularly in that space of spatial machine learning. So there are really a lot of resources. If you go to esriurl.com/spatialstats, a lot of the techniques and the topics that we talked about today are covered in much more depth in workshops and PowerPoints and tutorials that you can find there. There's a couple more workshops left, although we've crossed off quite a few this week. which I'm not sad about. We're making our way through. It's been a really great week. I know I've seen a lot of you all week, so that's great. I will one more time point you towards the survey. It's digital now, it's on your phone. You just search for this session. You can go through, very quickly fill out that survey. We really do get those results. It's kind of like Christmas morning, the day that we finally do get the results. We get very excited to get your feedback. And we very much appreciate you going in and filling them out. We really used to get a ton of responses when we put the session surveys on chairs and people would write in. And now that they're digital, we get very, very few, and data matters. So we are very passionate about using the data that we get from you to make our sessions better, and that's how we decide which sessions are even going to get put on each year. So if you do have some time, we know you're very busy, but we would definitely appreciate you filling out one of those course surveys. And with that, I guess thank you, and I hope you have a great rest of the conference, and we'll see you around. Thanks, guys.